Hey folks, this is Todd Coburn with your Aerospace Structure series. This is the Statics series, Lecture 3, where we're going to look at statics of particles again, but this time we're going to look at resolving forces using rectangular two-dimensional components. Let's see how it works. Last lecture, we saw how to resolve forces, the components of a force, by just taking a look, sketching out what lines of action we wanted the components on, and then using the parallelogram law to set up our force triangle, which we then utilize the laws of sine and cosine to solve for the components. Often, however, it's more convenient to use rectangular coordinates. Sometimes that force triangle, law of sine and cosine, is the key to solving it easily. But for many other problems, using rectangular coordinates is much easier. We're going to need to gain experience in figuring out which one is more efficient for solving the problem. And sometimes we'll start down one path and then have to change directions to solve with another method. When we're using components of forces, it's good to recognize and remember what we've learned in the past about unit vectors. In 3 space, we can define the unit vector. In the x direction, we call it I. In the y direction, j. In the z direction, k. So we have an ijk set of mutually perpendicular vectors which can completely define any vector in 3 space. Today, this lecture, we're going to be focusing on two-dimensional vectors, or vectors that lie in a single plane. A large number, most of the problems we're going to solve in engineering can be idealized as lying all those vectors in a plane. Either they actually lie in the plane, or we can pretend they lie in a plane with only a minor loss of accuracy. So we're going to focus on those kinds of problems first before we go onward to 3-dimensional problems. When we're dealing with 2-dimensional problem, we're just going to have that I and j component of force. Now, once again, the difference between what we're covering here today and what we covered in the last lecture is the idea that the two axes that we're going to get the components on have to be mutually perpendicular. If they're not, we need to go back to sine and cosine in order to solve the problem. But if we define two mutually perpendicular axes, actually they can have any orientation as long as the two axes are perpendicular, we can use these rectangular components as an easy way to solve it. Often for the problems we're going to see, we're going to be identifying our coordinate system as the x, y, and later in the z direction as well, which means that the I is typically in the x direction, the j is in the y direction, and so on. So let's focus on a vector here. We see this vector F, this red vector from Beer and Johnson. It's out located in a two-dimensional space, and we can see we have an x and a y coordinate. So it's convenient to use that x and y coordinate as our coordinate axes and define the coordinates of the components of the vector using those coordinates. We can say that we can see that this vector is going to project itself onto the x-axis. F cosine of that theta will give us that x component of the vector. F sine of that angle, theta, will give us the vertical component or the y component. If we want to write the vector force, we'll put an F. Often we will use a overbar or a arrow on top, or sometimes bold print, to define it and draw attention to the idea that it's a vector. And then we're going to say that it's actually got components, fx and fy, both of which are also vectors. Recognizing since those are vectors, these have to be put together with vector addition rather than standard addition, which means the parallelogram law or careful consideration of the different components. So we can say that that vector f is a function. It's got the vectors f in the x direction and f in the y direction. Now, we can then, since we're going to define our unit vectors, remember a unit vector is just a vector of magnitude 1 in a certain direction. So I, in this case, will define along the x-axis. J will define in the y-axis. And the only difference between these and the axes is just a line that extends onto anywhere, while that unit vector is just a line in the same direction, but of only of magnitude 1. We should learn this back in our physics or earlier classes. Since we've defined our unit vector of magnitude 1, I and j in the x and y directions, we now can write our force vector as a function of those unit vectors. So we can say that vector force F is the magnitude of the x component in the I direction plus the magnitude in the y direction times the j unit vector. And that defines the total vector F. Fx and Fy are now scalar components of that vector, and the I and the j define the representative directions that those two components are going in. So this completely identifies the vector. So this is not only this nomenclature, so we can actually put these together using scalars, just keeping track of the x component and the y component, and put them together in a table or something. But we're going to find that it's really useful, especially as we get to harder and harder problems, and especially to three-dimensional mechanics, space mechanics. It's very useful and helpful to utilize these I and j unit vectors to define that vector force F. And we'll look further into that as we go forward today and later. Okay? So once again, our total vector, that vector F, is defined by the magnitude of the x direction times I, the unit vector I, plus the magnitude in the y direction times unit vector j. Great. So now, to find the resultant of 3 or more concurrent forces, remember concurrent forces means the lines of action of all of them go through a point, any point. If all 3 vectors go through the same point, that makes them concurrent. And now we can solve for them using the methods of last lecture or this lecture. So we see if we had used the methods from last lecture, we would have taken 2 of these, put them together with our force triangle, and then we would have taken the resultant with the next component and done it again. But with rectangular components, it's even easier because we can just define each force vector with its components and the unit vectors, and then put together those component forces. So R, that resultant, now we're talking about that R is actually an equivalent force because we're taking all these forces and we're coming up with the equivalent force that they generate. So R is going to be P plus Q plus S, which means we're going to take the x component of R times the I plus the y component of R in the j direction is going to be equal to and you'll notice that each of these, we're just taking the p vector and we're taking the x component times I plus the y component times j. The next vector, we have an I and a j component. The next vector, we have an I and a j component. When we then add them together, we can use regular addition as long as we only put together the components that are in the same direction, which means we take all scalars that are multiplied by an I and we put them together. That means px plus qx plus sx, whatever that summation of those scalars are in the I direction. And then we're going to collect all the terms in the y direction, py, qy, and sy, all those times the unit vector in the j direction. And this completely defines the vector. Another way to do this is just add those scalars together, those scalars in the x and those scalars in the y. This is very useful, it's very practical, it's very easy to implement, and it's how most of the analysis of this type is done in industry. Okay, once we have the 2 components, we can get the magnitude of the resultant by simply taking the square root of the sum of the squares. And so our x squared plus our y squared, square root of all that, gives you the magnitude of r. And to get the new angle with the horizontal, you take ry over rx and take the inverse of the tangent of that, since the tangent of the angle is the opposite over hypotenuse. This is very straightforward. The thing we got to watch out for is keeping track of The vertical over the hypotenuse here for that angle is because that angle is defined between r and the x component. If the angle had been defined between the resultant and the vertical, then the cosine of that angle would have been the horizontal component actually, and the sine, they would have been reversed. So you got to keep track. You need to be strong on trig. That's not very hard trig, but you need to keep track of that trig and not just blindly apply these formulas without carefully evaluating those components. So that seems like a baby step forward, and it actually is. But there's a whole world of problems surrounding implementing that kind of analysis. Not problems, but different types of applications where we might see this used. So let's look at some examples to make sure we understand it. You're going to make sure you studied Lecture 2 enough to really be able to nail those components using sine and cosine. And now we're going to use Lecture 3 to evaluate those rectangular components using unit vectors. Okay? So here's our first problem, sample 2-3. This is out of Beer and Johnson. We've got 4 vectors here. This is the easiest kind of problem. It doesn't matter how many vectors there are. You'll notice they're all concurrent because all lines of actions go through a single point, that point A. You'll notice that we have the magnitude and the direction of each one. This means all we have to do is plug and chug, calculate x components, calculate y components, add all the x components together, add all the y components together. It doesn't get any easier than that. Let's see how it works. So we got 4 forces acting on bolt A. We're going to define the resultant force on the bolt. No problem. We're going to resolve each into rectangular components. We're going to then keep track of those and put them together. A easy way to do this, now you can just do this with longhand algebra on your page, but for these kind of problems, it's easiest to set up a table. Keep track of each force. We got force 1, force 2, force 3, force 4. We put it in the first column. In the second column, put the magnitude of each because that was given. We've got 150, 80, 110, and 100. Great. Being careful to make sure that each one is associated with its particular force. We then calculate the x component. And we're going to do this with respect to the same angle. So we need to be careful here. In this case, when we look at vector 1, we see force 1, which is the blue arrow going off this way. We have the angle of that. Now, actually, what might be useful in this table is to add one more column between magnitude and x component and put the angle that the force makes with the horizontal, the positive horizontal. That first angle makes a 30-degree angle, so we can just take the cosine of that resultant and the sine times that resultant to give us the 2 components. When we get to our second vector, that's going over here. There's 2 ways we can do this. We can do exactly the same way using the angle that this makes with the positive horizontal, which means what angle does that one make? That one makes 20 degrees. I'm going to back up here. 20 degrees with the vertical. So that means 90 plus 20 would be the angle, and we can plug in cosine of that and sine of that and just plug in those magnitudes here. Or you can use that 20-degree angle with the vertical and recognize that the sine of that angle is going to be the horizontal component, and it's in the negative direction. And the cosine of that is going to be your positive vertical component. That's a more intuitive way. The other one is more a plug and chug way. So we need to keep track of that and carefully use it. When we get to the third vector, it looks like that's straight down. So we're going to get only a vertical component. So it's just the magnitude of that in the negative y direction. Remember, we're talking I and j are both in the positive direction. Anything that's the opposite direction of those unit vectors will be a negative. And then our vector 4, which makes an angle of, it looks like negative 15 degrees. If you plug in negative 15 degrees, take the cosine of that times the magnitude of the resultant. And then that's your x component. And then the sine of that times the resultant will give you the other component. Or you can just say it's a 15-degree angle and recognize that that's a positive for the horizontal and a negative for the vertical, since that component is going to be acting downward. Once again, we're talking equivalent forces. Each of these forces, F1, F2, F3, or F4, are equivalent to the component forces, which is 129.9I plus 75J for the first vector. For the second vector, it's minus 27.4I plus 75.2J, and so on. Then we can just sum up the x component, sum up the y component. That will give us the two components of the resultant. And then to get the magnitude of the resultant, we take this squared plus that squared, square root of all that. And to get the angle, we take the y over the x, take the arctangent of that, as we're going to see here. And that's how we solve that. Got it? It's useful to, and Beer and Johnson is big on this, to reflect and think about the solution, think about what you did, think about how you solved it, and think about how you will recognize this kind of problem in the future and go through that, and so you can select the same solution procedure. Now let's look at the equilibrium of particle. In the earlier slide, we talked about looking at vectors and coming up with equivalent resultant, which is talking equivalent forces. We have a set of forces, and we're coming up with the equivalent single vector force that equates to that. The other idea is the idea of equilibrium, going back to Newton's law in lecture 1, action-reaction pairs. If we push against the wall, if it's not moving, it's pushing back with the same force. We can use this principle to solve a wide range of engineering problems. Anytime we have a balanced system, we can implement this principle. We'll have a couple classes of problem. One is when we have a bunch of forces acting on something and we want to know the equivalent force. Another one is when we have all the forces acting on something and we want to know the reaction, or what's pushing back or pulling against. In that case, we're going to come up with the equivalent force and then take the negative of that by summing our forces to zero. So going back to Newton's principle, we can say when the resultant of all forces acting on a particle is zero, the particle is in equilibrium. Another way to say this is basically what we're going to do here is we're going to say we always have, remember we had in lecture 1 we talked about static problems and dynamic problems. In this class we're dealing with static problems. That's arrow 2041 and in Cal Poly, and you can insert whatever your class number is. For dynamics, it's arrow 2150. That's the dynamic course, and any other. So basically, in most undergraduate programs, you're going to have a statics course where you're solving this kind of stuff, and a dynamics course which will follow. Remember, we're always dealing with the sum of the forces. And remember, our basic principle is that the sum of the forces is equal to ma. Mass times acceleration. This is Newton's law, and this is the basis of everything we're going to do in both of these classes. When we're in a statics course, we're going to say, hey, whenever we sum our forces and they're equal to zero, that means we're static, which means we're not moving. Whenever our sum of the forces is not equal to zero, that means it's actually equal to ma. That means we're going to get an acceleration. The sum of the forces divided by the mass is our acceleration. This is our next class. Since we're in statics course right now, what we're focusing on is all those problems that aren't moving, or they're continuing moving with constant velocity, which basically means they're not accelerating. If they're not accelerating, then the sum of the forces, then the acceleration will be zero. When we have ma, the sum of the forces is going to be zero, which means the acceleration is zero. That means whenever we're in statics class, we're going to be imposing the sum of the forces equals zero. That's required whenever we're not moving. Since we're focusing on non-moving problems, we're going to always be setting that to zero in this class. Once we've mastered all principles associated with statics, we're then ready to move on to looking at when the sum of the forces doesn't equal to zero and what happens then, how the equation, the motion of the member is changed. because of this, when we talk about imposing equilibrium, we're going to say we always have our forces, sum of the forces is equal to MA, and since A is 0, we're in a static problem, that means equilibrium means in statics, equilibrium means sum of forces is going to be imposed to 0, and in dynamics, equilibrium means we're going to be imposing this F equals MA kind of equilibrium. This is static equilibrium, this is dynamic equilibrium. This is next class, this is this class. Got it? So when we say, hey, the sum of the forces on all particles is 0, we're saying, hey, we're in statics class, therefore, when we sum up all forces, they have to be 0. Now, a point is we've dealt with in the prior couple slides, we talked about the resultant of all those forces. What we were looking at, we were focused on, hey, we've got all these forces acting. We're not looking at a complete system of forces. We're just looking at a subset of forces that are applied to something, and we're looking at the equivalent force. That's why we didn't sum the forces to 0. We're just trying to figure out what's the cumulative effect of these applied forces. Now, when we draw a free body diagram of the member, we then will have not only the applied forces, but the reactive forces. And once all forces on the point, particle, or member have been assessed, we know they have to sum to 0. So far, we have been talking about particles. We're not yet looking at rigid bodies, which means we're looking at a point. And on that point, we have a bunch of forces acting. And that is just a set of forces that we can turn into a resultant. However, if we draw a free body diagram of the thing, what a free body diagram is, it's a figure that includes all forces, both action and reaction pairs. Remember in our first or our second lecture, we had a picture of some dude pushing on a door with a force. And if we want to know the summation of all the applied forces, we could sum those up and come up with resultant. But if we drew a full free body diagram of the whole system at the point where contact is happening, we would have his force that he's applying. Let me redraw it. We would have the door, we'd have the force that he's applying, and we'd also have the reactive force that's the door is pushing back. This is called a free body diagram because we've taken that point, we have drawn all applied forces and all reactive forces. We have taken the door, we've removed it. We had the force on the door. Now we're focusing on this point of contact. We have the force on the door at that point, and now we're going to remove the door and we're going to replace it with all the forces that is pushed back. And usually we're going to call that R for resultant. So at this point, we have this force is the sum of all forces applied, and this is the reaction that represents the door's action. Since this is now a free body diagram of this point A, where contact is happening, we can impose equilibrium, which means we're now going to take the sum of the forces in each direction. We'll start with the sum of the forces in the x direction. We can say in that direction is by this. My pen doesn't look very nice. Let me redraw it. The sum of the forces in the x direction, we're going to call this positive. It has to be equal to 0 since we're a static problem. That means we've got F, that force, which is in our assumed positive direction, minus R, because we're plus R, but R is in the opposite direction. They have to be equal to 0, and we can now use this principle to say that then R is equal to F. Now we'll say it's equal to F. Obviously it's in the opposite direction, but we accounted for the directions here by assuming this was positive. This is in the positive direction, this is in the negative direction, so when we solve for the magnitude is positive. Now if we had actually misdrawn this and said F, and if we had drawn the reaction here, we would have summed our forces in the x direction equals 0 in the same way. We would have said F plus R equals 0, and we would have found out that R is negative F, which means R has the same magnitude of F, but it's actually in the opposite of the direction, that, or we could draw like this, R equals whatever the magnitude is, F in that direction, the opposite direction. That's a way to do that. Got it? So in this particular problem here, where we're talking about imposing equilibrium, we're saying when the resultant on all forces is 0, the particle is in equilibrium. What we're saying is we're going to draw a free body diagram of the particle with all the forces, the applied forces, which is the action forces, and the reactive forces. And we're going to sum them up. Since we're in static, we're expecting this not to move. We're going to impose equilibrium, which means we're going to say that they have to be equal to 0, and we're going to use that concept to solve for our forces. When the sum of all forces acting on a particle is 0, the particle is in equilibrium. Now, when we get to dynamics, we're going to find out in order to impose equilibrium, we're going to take the sum of the force equals ma. We're going to subtract the ma. That makes it sum to 0 again. We'll deal with that next semester. Right now, we're saying sum of the force equals 0 because we're static. It's in equilibrium, and it's also not moving. We said this. Therefore, at part A, at particle A, if we have an applied force, let's say that this force up here is applied, then this force here is a reactive. What we do is we draw the force, the point, the particle. We draw our first force, and we would label 100 pounds. That's our applied force. And then we say, okay, we've got some component that's reacting against it. We can see, since action-reaction pairs, we can draw this in the opposite direction, and we can see by inspection that when we sum the forces along this line, that this reaction is going to be completely equal. This particle has two forces acting on it. They're equal magnitude, same line of action, opposite sense. That means this force is completely balanced by this force. This particle is in equilibrium. It is experiencing tension. We're going to learn about that in our Structures 1 or Strength 1 class, but the particle itself is in equilibrium because all the forces on it are completely balanced. Got it? So if we have a particle like this one at the left, let's say we focus on this particle here, and this particle looks like we have 1, 2, 3, 4 forces. We can impose equilibrium, which says, hey, if these are all of the forces, action and reaction forces acting on this point, and if the point is not accelerating, the sum of all those forces better be 0, according to Newton's first law. So we can sum up all forces and set them equal to 0 and solve for any unknowns. We can see we've got a 300-pound force in the x direction. We have a 400-pound force, which has components in the positive x and, negative x and positive y. We've got a force of 200 magnitude, which has components in the negative x and negative y. And a force of 173.2 pounds in the negative y direction. We can sum up all our x components. Those have to equal 0. Sum up all our y components. Those have to equal 0. Why do they have to equal 0? Because we said this particle is not moving. If it's not moving, those better sum to 0 if they're all forces. How do we solve for them? Well, you can either combine them tip to tail and make sure they go back to the same point. That would be the same as showing that all components go to 0. Or you can come up with the components, come up with the x and the y component of each, add them all together and set each component has to be equal to 0 if that vector is going to be, if that particle is going to be non-moving. That's what imposing equilibrium means. Got it? Okay. Let's look at some examples then. Here's a common example. Here what we have is we have a truck. And we see that we got a box being lifted. And it's being lifted by 2 cables, and some men are pulling on the cables. Now, whenever we see a problem like this, there's a few things we're going to need to recognize immediately. Whenever we see a cable can only hold tension. It can't hold compression. It can't hold shear. That means the forces along the cable will be along the lines of action of the cable. We can cut the cable anywhere and evaluate the forces at that point. For example, if we were to cut this, if we call the tension in this cable, let's call that T1. If we cut the cable here, we can see that that cable is going to have a tension of T1 on both sides. We got the part down here in the little man's hand, and we get the part up there, and both of these are in, we could cut this one, and we could see, looking at this part of the cable, we could see that's in tension of T1, and looking at this part of the cable, that's in tension T1. If we cut this cable, we see that one, if it's in tension, that would be T2, and if we cut it over here, we can see that this one is in tension here, okay? The cable is just carrying tension. The next thing is, whenever we see a pulley like this, we're going to imagine that that pulley is frictionless. The way a pulley works is this cable is going to go up and over the pulley and pull off in some other direction. What the pulley does, it allows us to change the direction of a force. You can see that this force of tension T, and this is also tension T, but it effectively changed the direction. This T only had a Y component of force. This T has an X and a Y component of force. Got it? So whenever we look at this pulley, we're going to assume that it's frictionless. Now, if it wasn't frictionless, then friction could change the tension from one value to another value. We'll deal with that when we get to friction later. Right now, we're dealing with most of these problems we're going to see until we get to friction. We're going to assume frictionless pulleys and frictionless everything else. What that means is when we focus on this problem, we can say, well, whatever force this guy is pulling down is the same as the tension in this cable anywhere. And the force that this guy is pulling down is the same as this tension anywhere. We can see, even though this looks rather complicated, this box has a certain weight, and this cable here is going to be carrying exactly that weight if it's lifting the crate. Everything else can be ignored in this problem. So we're going to end up, the key to this problem, after we recognize those principles, is we're going to take this point A, and we are going to draw a free body diagram of that point, which means we're going to redraw that particle A, and then we're going to draw all forces acting on it. We see, if we look at that, we've got a force in the direction of this cable, shown here. We've got a force in the direction of this cable, shown here, and a force in the direction of this cable, shown here. So this one acts straight down, this one acts 30 degrees above the horizontal, and this one acts at 50 degrees above the horizontal, and the orientation of all of these are tension since these are cables. If we fail to recognize the idea that those pulleys are frictionless, that the cables carry only tension, that we're going to focus on a particle, all forces going through the particle, and that the cables are carrying only tension, and that the sum of those forces are going to have to be zero if that's all forces acting on the particle, all action and reaction pairs, then for that to be an equilibrium, which means static equilibrium, which means it's not accelerating, the sum of any and all components has got to be zero, which means the sum of the x components better be zero, the sum of the y components better be zero, and we're going to use that principle to solve this mother. Got it? If we fail to recognize any of those things, then we will fail to solve the problem correctly, regardless of how good we are at algebra, because our foundation is bad. One of the key principles we need to learn as engineers before being allowed onward is that we understand how to quickly and efficiently and clearly draw a free body diagram of any particle, rigid body, or anything else. Right now we're focused on particles, so we're going to be drawing free body diagrams of points. If we fail to master this concept, it will undermine our potential to understand when we get to rigid bodies, which will undermine all of our work in dynamics, all of our work in structures 1, all of our work in structures 2, and really the rest of our engineering careers. Do yourself a favor. Spend as much time as you need to master this principle before you move on to the next lecture, so that you're building on knowledge rather than building on sand. So once again, we see this problem, we recognize, great, we have point A, we're going to draw a free body diagram, which means we've got a tension here, tension here, tension here. We're going to identify those angles carefully, and then we're ready to solve. Sum of the forces in the x direction better be equal to 0. And then we can solve the sum of the forces in the y direction equal to 0. And follow with the algebra until we solve this problem for all unknowns. That's what we're going to be seeing and implementing over and over and over again in statics class. Got it? All right, let's look at a similar problem. This time we're going to put numbers on it. Here's a very similar problem. Now we have this ship that's unloading a car. Once again, there are a number of keys to this problem, but we need to start with the easy stuff. We need to recognize that the forces are going to be concurrent right here at point A. Whatever this car weighs, it's going to be loading up this cable right here. So we're going to have a force like that. So we draw our point A. Okay, first, this first little cable is coming down, and that's going to be whatever that automobile force is. In this case, is 3,500 pounds. Got it? So we see the car is 3,500. Now you look at this, you say, wait a minute, it's pulling here, what's it doing up there? Well, actually, it doesn't matter because you realize whatever it's doing, if you look at the lower part of this, here's point A, here's where this splits out, and it's holding the car and all this crap here. But regardless of what it is, this is 3,500 pounds. It's not rotating, it's sitting still. That means if we cut this, this is pulling up exactly 3,500 pounds. Now we're going to skip all of this and we're going to go straight to recognizing, well, if that little piece is in tension, we can go straight here and draw our little 3,500 pounds. Let me erase this and start over. Now that we understand that concept, run it back, the video back if you don't understand that. So once again, we're focusing on this point because we've got forces along this tension, and along this direction. All of those are concurrent. They're all going through that point A. That's where we're going to do our free body diagram. Let me redraw that because I don't know why this Wacom bleeds like that, but it does. So here's our point A. We've now got the downward force aiming toward the car. That's going to be 3,500 pounds. It's straight down. We're going to have this force along this deal, which if we draw that, we see that makes an angle of 30 degrees with the horizontal. So we're actually, what we need to do, and we'll call that tension AC. What we want to do is draw each force vector and draw it with the angle to the nearest convenient axis, which is generally the horizontal, the vertical axis. That one makes a 30-degree angle. And then we see this other one. Now, if we look at this, we say, oh, wait a minute, this is tricky. We've got, this is the vertical, and this is some angle. If we draw a vertical here, we see, oh yeah, going back to last lecture, remember those Z's? That means this angle is equal to that angle, which means basically we can say, okay, if this is the vertical, Y, this is going to make this little angle 2 degrees with the vertical. That's the direction of that tension. That's TAB. You'll notice it's very common and convenient to define tension in a cable by its endpoints. So we've got AC. This is a line segment AC. It's actually a vector. You could call it a segment or a vector. But when it's a force, it's actually going to be a vector, and we can call it TAC, which is a vector, so we could draw a little arrow above it if we want. We've got this other one going off in this direction, which was 2 degrees from the vertical. That was T, and that's AB. Now, you could call it BA, but I like to call it in the direction of the positive. So AC is acting tension from A to C. AB tension will be acting from A to B, so I'd call it tension in the AB direction. And then we've got this little car weight, which since we don't have a little arrow, we can just say that that's 3,500 pounds, and that's straight down. Got it? This is all forces now acting on A, so we're going to impose equilibrium. We're going to say, okay, sum of the force in the X equals 0. That means, we'll call that positive. That means we're going to have TAC cosine of 30 degrees, right? That's going to be this component. If this is perpendicular, minus, and we've got this little guy, TAB, cosine of 2, or excuse me, that actually, if we're using this 2 degrees, cosine will give us this, sine will give us this. So we're going to use sine of 2 degrees. And that's going to be in the positive, that's in the negative direction because the component, you'll notice this component is going to have a component like this and a component like that. There's a component like this and a component like that. So for x, we've got positive for the first component, and this one's going in the negative direction, and those have to equal to 0. We can now say, okay, great, we can't solve that yet. What we should have done first was sum our forces in the y direction. We'll call upwards positive, they have to equal to 0. So now we're going to have is TAB times, now we're going to do cosine, because cosine, since we're going to use this angle here, cosine of that angle will give us this component. Cosine of 2 degrees, it's a positive, and then we have this minus 3,500 pound force, and then we have this other one, minus TAC, and actually that's going to be sine of that 30 degrees, that equal to 0. We now have two equations. We have this equation and we have this equation. We can solve this equation for one and say solve for TAB, and then plug in what we find in here and then solve that combined equation. That's what we're going to do on the next slide. We're getting a little ahead of ourselves to kind of lay out our process. Got it? So we're going to construct a free body diagram at the point where the forces are concurrent. That's point A. We're going to apply our conditions of equilibrium after we've carefully drawn all forces acting through that point to impose equilibrium, static equilibrium on that particle. And then we're going to apply trig, which means using either a law of sines, cosines, or rectangular components with the ij. Okay? So here we see on the left, we've drawn the free body diagram of point A like we did on the last slide. And then we can either use components like I just talked about, or we can construct our force triangle, which means if that's an equilibrium, then that means we can take these head to tail and put them together, and they have to be equal to 0, which means they close that triangle, which means we can take any of them first. Let's take TAC, as we see here, traverse, and let me draw this. We're going to go from point A along TAC, and then we can take TAB on, stick it from the nose to its end, and then take that 3,500, which is going straight down, that has to close the triangle. We then can translate. We can say, okay, this little angle here is 2 degrees. This little angle here was 30 degrees from the horizontal. Let me draw it with a pen. This little angle here was 30 degrees from the horizontal, right? So actually, when you add that to 90, we've got 120 for that angle. And then we can actually, and this other one is acting straight down, remember? And now we can calculate any other angles. We knew this was 2. And we just calculate this to be 120. So we can say, okay, 180, since that has to sum up to 180, right? Minus 2 minus 58, minus 120 gives us that 58 degrees there. Now we can either use those rectangular components, which will give us 2 equations to solve, or we can use law of sine or cosine to solve this, as we saw in the last lecture. Okay? So in the text uses the law of sines, fine, and that allows us to solve for that TAC directly. And once we have that, we can solve for TAB as well. Okay? This is a very classical problem. There's a whole family of different problems that will look differently but really be the same principles. Basically, it involves locate the point where the forces are concurrent. Draw all forces on the point. Impose equilibrium, which means sum your components, or draw your force triangle so those forces all close on 0, and then solve for the different pieces. Here's another problem. Another classic problem. We saw a problem similar to this last lecture. Here's a boat. This is also from Beer and Johnson. We have 3 cables attached to the boat. One of them is a vertical cable, vertical on this picture anyways. Another one is an angle beta, another one at an angle alpha. We can identify quickly that the point that we're going to need is we're going to see point A is the key because all forces are concurrent. Now before we go too far, let's think about this together. We're going to focus on this point A where all forces are concurrent. You'll notice we have this tension in this cable, TAC. We've got this tension in this cable, TAB. We've got a tension in this cable, TAE. And then the other thing you might not notice, since the flow is going this direction, what that's going to do is cause drag on this boat such that the force of that flow is going to cause a force in the horizontal direction like this. Okay? When we read the problem, we see blah, blah, blah. The tension is 40 pounds in cable AB, so we have this guy known. And 60 in AE, we've got this guy known. This is a common problem where we have, let's say, we just have a boat and we have 3 cables attached and we have some flow that we don't know how much force, how much drag is occurring. We can just measure how much tension is here, how much tension is here, how much tension is here, and that will allow us to calculate precisely how much drag we're getting from the flow. In this case, we have 2 knowns and 2 unknowns because it looks like we don't have, let's see what else. Blah, blah, blah. 60 pounds, excuse me, we have 60 pounds in AE. We have a certain amount in AB, 40, 60 in AE. We want the drag force, this one, and the tension in cable AC. Great, no problem. We're going to focus on the point where all forces are concurrent. We're going to draw all forces. We've got this one at an angle beta. We've got this one at an angle alpha. We've got this one along the horizontal. We'll call this D, drag. And we've got this one in this is TAE, this is TAC, this is TAB. We've identified all directions, and now we're ready to solve this. We can either put these together with a triangle that closes on itself, which means this plus this plus this plus this is going to close on 0. Or we can sum forces in the x equals 0, sum forces in the y equals 0, and solve it that way. Either one will work. We have 2 unknowns and we have 2 equations. Since it's a particle, we can sum our force in the x, we can sum our force in the y. That's 2 equations. We have 2 unknowns, those 2, the drag force and that TAC force. That's the method we're going to solve for this and all problems of this kind. So this says blah, blah, blah. We talked about all this, okay? Let's take a look at the numbers. So here's that force triangle we talked about. And then we can go and use any trig to identify any angles that we don't know. And then we can solve our problem. Let's go back up. Oh, let's see. If we go back up here, we'll notice. Here's another thing that we needed to notice here. Notice here that we had those angles. We weren't given those angles, were we? We weren't given the alpha and the beta. We were only given dimensions. You've got this dimension, you've got this dimension. And because of that, we know there's actually a whole class of problems like this where when we're going to know endpoints of cables, but we don't necessarily, it's more convenient to measure distances than it is to measure angles. So we see this cable is 4 feet in the vertical. Now the problem here is whenever we see these things in feet, remember we're going to do all stuff in the pound-inch system. So we're going to have to convert that into inches, right? 4 times 12 to get the number of inches that this is. We've got this 7 foot, we convert that to inches. So for this cable, we know at this dimension and this dimension, this is 4 feet, this is 7 feet. we're going to need this dimension, and then we can calculate what this alpha is. This is 4 feet, this is 1.5 feet, and we can now use trig to solve that. That's what we're doing on the next slide first, is getting those angles so we can solve it the way I suggested we be solving it. So here we say okay. Now they're not converting these to inches yet because they're saying, well, actually, because these are both in feet, we can use that relative distance. That will have the same ratio as if we had converted it to inches first, because we'd have a 7 times 12 over a 4 times 12, same diff. So the tangent of the alpha is 1.75. We get the alpha of 60 degrees roughly and the beta of roughly 20 degrees. And then we can use those in our calculations. We're now ready to sum up our forces. We know the total resultants can be all those. They have to sum equal to 0. This is actually a little sloppy. What we should be saying is either we're going to do tip to tail and make sure it closes back on itself, or we're going to do sum of the components in the x, sum of the components in the y, and set each of those components to 0 to solve for the unknowns. Okay? And that's what they're doing here. So TAB is going to be its magnitude sine of this angle. It's this angle, so the sine of this angle is actually going to give us a horizontal component, so that's going to be times the I. It's in the negative I. We've got that 40 again, and the cosine of that angle, which is going to be this component, which is going to be in a positive J. We will look at TAC, that's here, and we have this angle. So the cosine of this is going to be this component, which is positive J. And the sine of that is going to be positive I. For TAE, that's just got a negative J component. And what else are we missing? 1, 2, 3. And the drag, which is in the negative I direction right here. Okay? That means the total resultant, if we sum all that up with knowns and unknowns, we get this. We can set all these components. And the way we do that, we can actually just say sum of forces in the x equals 0. Call that positive. And we say this plus this equals 0. And we end up with 2 unknowns. Solve for one of them. And then say, okay, now the sum of the force in the y direction equals 0, which means this plus this equals 0. We can actually do this one first, and that will give us TAC, and then use that TAC in this equation to solve for our other force. Got it? Or you can draw the force triangle and do it that way. Okay? So study this out, try it on your own, make sure you can do this, because there's a whole class of problems that focus on this kind of method. So you'll notice last lecture, lecture 2, and this lecture, lecture 3, basically cover the same kind of method. Last lecture focused on resolving into any components. Today we first focused on rectangular components, and then we started focusing on solving problems. Beyond just calculating equivalent force systems, we started imposing equilibrium. Equilibrium on the particle, which means if we have a particle, we've drawn all forces on the particle, and if that particle is in equilibrium, the sum of forces in any direction is equal to 0. Sum of force in the x is to 0, sum of force in the y is 0. Later we'll find out when we go to 3 dimensions, we're just going to have one more direction to sum. Okay? Now later, when we start dealing with rigid bodies, we're going to have moments as well. It's going to get harder. So it's critical that you master this lecture and last before turning the page to lecture 4. Practice these problems. If these problems aren't enough, I recommend getting a hold of a Beer and Johnson Mechanics of Statics vector book. Or Hibbler's book is good. Miriam and Crage's book is good. These are all good books. Actually, any undergraduate text on statics will be useful, and they will usually have a number of different example problems you can try and practice on. And then they'll have a bunch of problems, often with answers in the back. You can check yourself. If you're willing to invest the time, you can master this material. Got it? All right, go out there and be great, and I will see you once you've mastered this content in our next video. Enjoy. Well, be sure to subscribe if you haven't already done that to stay tuned with the latest, both while you're going through your engineering curriculum and beyond. When you get into industry, you will run into some of the problems that you practiced before, and you may find these videos are useful again if you're in a structural analysis career. Enjoy.